Hey everyone, and welcome back. Get ready because today we are diving right into the heart of mechanics of materials. We're talking about how things actually hold together, or, how they break. We're jumping into section 1.2 of Jere and Timenko's classic textbook. This is gonna be fun.
All right, let's do a super quick recap. Last time, we learned that mechanics of materials is basically the science of how stuff reacts to forces. It's absolutely essential for designing everything you see around you. We also talked about how engineers use two paths, tinkering and thinking, and two types of solutions, master recipes and one-off calculations. Got it? Good, because we're about to put those ideas to work.
Because today, today, we are pulling back the curtain on the two biggest, most fundamental secrets in all of engineering. I'm not kidding, almost everything that gets built relies on these two concepts.
And those secrets are stress and strain. Now, I know they sound kind of heavy, maybe a little intimidating, but I promise you, stick with me for the next few minutes, and you'll see just how simple and honestly how cool these ideas really are.
First up, stress. The best way to think about it is to imagine what a material feels on the inside when you pull or push on it. That internal pressure, that resistance, that's stress.
To make this super clear, let's forget about steel and concrete for a second. I want you to picture this bar here as a giant, stretchy candy bar, like a big Tootsie Roll. Now imagine we grab both ends and pull. What do you think is going on deep inside that candy? Well, that pull on the outside wakes up an army of tiny internal forces that fight back. And if we could magically slice that candy bar in half, you'd see that force isn't just in one spot. Nope, it's spread out evenly across the whole surface, like every single molecule is holding hands and refusing to let go. And that right there is our first big idea. We call the intensity of that internal force normal stress. We use the Greek letter sigma for it. You can basically think of it as a way to measure the material's collective ouch. So how do we put a number to that ouch? The recipe couldn't be simpler. You just take the force that you're applying, we call that P, and you divide it by the area it's spread across, we call that A. Force divided by area, that's it. That gives you the stress.
Now this ouch can happen in two ways. If you're pulling on something trying to stretch it out, that's called tension. We usually call that a positive stress. But if you're pushing on it, trying to squish it, that's called compression. And you guessed it, we call that negative stress. Pulling is positive, pushing is negative. Easy.
Okay, so we've nailed down the internal feeling, the stress. But all that internal drama causes something to happen on the outside, something we can actually see and measure. And that brings us to secret number 2, strain.
Right. I mean, it's a great question. All that internal battle, all that stress, it has to have some kind of visible effect, right? When you pull on something, it doesn't just feel it, it physically changes.
Let's go back to our trusty candy bar. When we pull on it, what happens? It gets longer, right? It stretches. Well, that total amount of stretch has a fancy name. We call it elongation, and we use the Greek letter delta to represent it.
But think about this. If I told you something stretched by 1 inch, is that a lot? Well, it depends. If it was a rubber band, maybe not. If it was a 1-inch long steel bolt, that would be insane. So what really matters isn't just how much it stretched, but how much it stretched compared to its original size. And that idea, that stretchiness, is what we call normal strain. And just like with stress, there's a super simple recipe. We take the total stretch, our friend delta, and we divide it by the original length of the bar, which we call L. That ratio gives us the strain. It's a way of standardizing the stretch so we can compare apples to apples. Okay, you're doing great. We have our 2 secret recipes, one for the internal ouch and one for the external stretchiness. Let's stop playing with candy and see how these tools work on a real-world problem. All right, here we go, a real-life example straight from the textbook. We've got a steel bar. We know it's being pulled with 70,000 newtons of force, and it stretches by 1.2 millimeters. The challenge is, can we use our new recipes to figure out the stress and the strain? I think we can.
First things first, let's find the stress. What's the recipe again? Come on, you know this. It's force divided by area.
Okay, the force is given as 70,000 newtons. The area, well, the bar is a rectangle, so we just multiply the width times the height. That's 40 millimeters times 20 millimeters. You run those numbers and boom, you get 87.5 megapascals, or MPa. A pascal is just a newton per square meter.
This is the unit engineers use all the time for stress. So when you hear megapascals, just think stress.
Awesome. One down, one to go. Now for the strain. How much stretchiness did that steel bar actually have?
The recipe for strain, remember, is the total stretch divided by the original length. We know it stretched 1.2 millimeters, and its original length was 2.8 meters. But wait, we need the units to be the same, so we convert 2.8 meters into 2,800 millimeters.
And that gives us a strain of 0.000429. Now you might notice something's missing. Where are the units? Well, since we divided millimeters by millimeters, they canceled out. Strain is just a pure number, a ratio. It tells you the proportion of the stretch.
And just like that, you solved a real engineering problem. You calculated both stress and strain. That's fantastic. To make sure these ideas are locked in for good, let's do a quick quiz and recap.
All right, pop quiz, hotshot. Let's say you're pulling a rope with 10 newtons of force, and the rope's cross-sectional area is 2 square meters. What's the stress in the rope? Take a second, think about the recipe.
Did you get 5 pascals? Because that's the right answer. It's just force, 10 newtons, divided by area, 2 square meters. See? You totally got this. It's not so scary after all.
So let's wrap up with the big takeaways. Number 1, stress is the internal pressure, the ouch a material feels. It's just force over area. Number 2, strain is the external stretchiness. It's the stretch divided by the original length. And remember, tension is from pulling, compression is from pushing. These two incredibly simple ideas are, no joke, the foundation for how we design everything.
But this all leads to a really interesting question, doesn't it? We know how to measure the internal ouch and the external stretch, but what's the connection between them? And more importantly, what happens when you pull a little too hard?
If you found this useful, do me a favor and hit that like button. If not, the dislike is there too. And please, drop any questions or thoughts you have in the comments below. I'd love to hear from you.
Because next time we're going to answer that question. We're diving into section 1.3 stress-strain diagrams, where we literally plot the relationship between the ouch and the stretch and find the exact point where things snap. Make sure you follow so you don't miss it.
Thanks for tuning in.